Hello students. Hello students. Today we are going to discuss valence bond theory and hybridization. This is Muhammad Jalil Ahmed, lecturer in chemistry, Dr. BRR Government Degree College, Jadcherla, MBNR district. Contents of the video lesson: types of hybridization, examples of hybridization, and structures of examples. Valence bond theory. The valence bond theory was proposed by Hitler and London to explain the formation of covalent bond quantitatively using quantum mechanics. Later on, Linus Pauling improved this theory by introducing the concept of hybridization. Valence bond theory assumes that all bonds are localized bonds formed between two atoms by the donation of an electron from each atom. Valence bond theory describes covalent bond formation as well as the electronic structure of molecules. The theory assumes that electrons occupy atomic orbitals of individual atoms within a molecule, and that the electrons of one atom are attracted to the nucleus of another atom. A covalent bond is formed by the overlapping of two half-filled valence atomic orbitals of two different atoms. The electrons in the overlapping orbitals get paired and confined between the nuclei of two atoms. The electron density between two bonded atoms increases due to overlapping. This confers stability to the molecule. Greater the extent of overlapping, stronger is the bond formed. The direction of the covalent bond is along the region of overlapping of the atomic orbitals. That is, covalent bond is directional. Valence bond theory explains the formation of sigma and pi bond. There are two types of covalent bonds based on the pattern of overlapping as follows. Initially, sigma bond. Sigma bond is a covalent bond formed via linear overlap of two orbitals. Pi bond. A pi bond is a covalent bond formed via parallel overlap of two orbitals. See, sigma bond is a covalent bond formed by linear overlap of two orbitals. Pi bond is a covalent bond formed by parallel overlap of two orbitals. It means that linear overlap or end-on-end overlap leads to the formation of sigma bond, which is a strong bond. Sidewise overlap or lateral overlap leads to the formation of a pi bond, which is a weak bond. The covalent bond formed due to overlapping of atomic orbital along the internuclear axis is called a sigma bond. It is a stronger bond and cylindrically symmetrical. Depending on the types of orbitals overlapping, The sigma bond is divided into following types: sigma SS bond, sigma PP bond, sigma SP bond. So there are three types of sigma bond: sigma SS, sigma PP, sigma SP bond. Let us see the formation of sigma SS bond. Sigma SS bond is a covalent bond formed by linear overlap or axial overlap or end-on end overlap of two s orbitals. S orbital of one atom overlaps along the internuclear axis with the s orbital of another atom, forming sigma molecular orbital. With the result, sigma SS bond is formed. Sigma PP bond is a covalent bond formed by head-on overlapping or end-on end overlapping between two p orbitals of two atoms. The extent of overlapping between two p orbitals is greater. According to valence bond theory, greater the extent of overlapping, stronger will be the bond formed. Therefore, sigma PP bond is a stronger bond than sigma SS bond. Now sigma SP bond. Sigma SP bond is formed by linear or axial overlap between s orbital of one atom and a p orbital of another atom. The extent of overlap between s orbital and p orbital is weaker than overlap between two p orbitals but stronger than overlap between two s orbitals. Therefore, sigma sp bond is a weaker bond than sigma pp bond, whereas sigma sp bond is a stronger bond than sigma ss bond. Pi bond. The covalent bond formed by sidewise overlapping of atomic orbitals is called a pi bond. In this bond, the electron density is present above and below the internuclear axis. It is relatively weaker bond since it is relatively a weaker bond since the electrons are not strongly attracted by the nuclei of bonding atoms. Formation of H2 molecule. The electronic configuration of hydrogen atom in the ground state is 1s1. In the formation of hydrogen molecule, two half-filled 1s orbitals of hydrogen atoms overlap along the internuclear axis and thus by forming a sigma SS bond. See the formation of sigma SS bond. During the formation of sigma SS bond, 1s orbital of hydrogen atom overlaps along the internuclear axis with the 1s orbital of another hydrogen atom, forming sigma molecular orbital. Now formation of Cl2 molecule. This is an example for the formation of sigma pp bond. The electronic configuration of Cl atom E in the ground state is neon 3s2, 3px2, 3py2, 3pz1. Cl atomic number 17. Its electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p5. In other words, 3s2, 3px2, 3py2, 3pz1. The two half-filled 3pz atomic orbitals of two chlorine atoms overlap along the internuclear axis and thus by forming a sigma pp bond. You can see 3pz orbital of one Cl atom, 3pz orbital of another Cl atom. Now, during the formation of sigma pp bond, 3pz orbital of one Cl atom overlaps along the internuclear axis with the 3pz orbital of another Cl atom, forming sigma molecular orbital. Since the extent of overlap is greater, therefore the resulting sigma bond is a stronger bond. HCl molecule. Formation of HCl molecule is an example for sigma sp bond. In the ground state, the electronic configuration of hydrogen atom is 1s1, and the ground state electronic configuration of Cl atom is neon 3s2 3p5. That is 3s2 3px2 3py2 3pz1. The half-filled 1s orbital of hydrogen overlap with the half-filled 3pz orbital of 3pz atomic orbital of chlorine atom along the internuclear axis to form sigma sp bond. You can see the formation of HCl molecule. During the formation of HCl molecule, 1s orbital of hydrogen atom overlaps along the internuclear axis with the 3pz orbital of Cl atom, forming sigma molecular orbital. Here the extent of overlap between spherical shaped s orbital and dumbbell shaped p orbital is somewhat greater extent than the overlap between two spherical shaped s orbitals. Since s orbitals are non-directional orbitals, the extent of overlap between two s orbitals is weaker. Therefore, sigma ss bond is a weaker bond than sigma sp bond. Otherwise, sigma sp bond is stronger than sigma ss bond. Formation of O2 molecule. The electronic configuration of oxygen in the ground state is helium 2s2 2p4, that is 2px2 2py1 2pz1. The half-filled 2py orbitals of two oxygen atoms overlap along the internuclear axis and form a sigma pp bond. The remaining half-filled 2pz orbitals overlap laterally to form a weak pi pp bond. Thus, a double bond, one sigma pp and one pi pp, is formed between two oxygen atoms. You can see the formation of a sigma pp bond and a sig pi pp bond between two oxygen atoms. Here, two separate 2p orbitals of each oxygen atom are shown. In the right hand side, formation of sigma pp bond takes place initially and formation of pi pp bond takes place finally. Ultimately, in between two oxygen atoms, a covalent double bond is formed. In that covalent double bond, one will be a sigma bond, another will be a pi bond. Thus, O2 molecule contains a multiple bond. N2 molecule, formation of N2 molecule. The ground state electronic configuration of nitrogen is helium 2s2 2p3, that is helium 2s2 2px1 2py1 2pz1. A sigma pp bond is formed between two nitrogen atoms due to overlapping of half-filled 2p atomic orbitals along the internuclear axis. N2 molecule. The remaining half-filled 2py and 2pz orbitals form 2 pi pp bonds due to lateral overlapping. Thus, a triple bond 1 sigma and 2 pi atoms. Here you see formation of N2 molecule. In N2 molecule, a covalent triple bond is formed between two nitrogen atoms. Initially, sigma pp bond is formed between two N atoms. This sigma pp bond is formed by axial or head-on overlapping between two 2p orbitals of each nitrogen atom. Later on, two pi pp bonds are formed by lateral or sideways overlap between the remaining two 2p orbitals of each nitrogen atom. Thus, a strong triple bond is formed between two nitrogen atoms so that N2 molecule contains a multiple bond. Now, hybridization. The phenomena of hybridization. The concept of hybridization will be discussed in detail. The intermixing of two or more pure atomic orbitals of an atom with almost same energy to give same number of identical and degenerate new type of orbitals is known as hybridization. This is the definition of hybridization. The phenomena of intermixing of two or more pure atomic orbitals of an atom with almost same energy, giving rise to an equal number of new orbitals of equal energy, is called hybridization. The new orbitals formed are also known as hybrid orbitals. During hybridization, the atomic orbitals with different characteristics are mixed with each other. Types of hybridization. There are 6 different types of hybridization. The sp hybridization, sp2 hybridization, sp3 hybridization, sp3d hybridization, sp3d2 hybridization, sp3d3 hybridization. Now let us discuss in detail one by one. Sp hybridization. Intermixing of one s and one p orbital of almost equal energy to give two identical and degenerate hybrid orbitals is called sp hybridization. These sp hybrid orbitals are arranged linearly yet by making 180 degrees of angle. They possess 50% s and 50% p character. You can see the formation of two sp hybrid orbitals. Spherical shaped s orbital mix with a dumbbell shaped p orbital, resulting the formation of two identical sp hybrid orbitals. Each sp hybrid orbital possesses 50% s character and 50% p character. Angle between two sp hybrid orbitals is 180 degrees. We also call it as linear hybridization. sp hybridization is also called linear hybridization. Now, sp2 hybridization. Intermixing of one s and two p orbitals of almost equal energy to give three identical and degenerate hybrid orbitals is known as sp2 hybridization. The three sp2 hybrid orbitals are oriented in trigonal planar symmetry at angles of 120 degrees to each other. The sp2 hybrid orbitals have 33.3% s character and 66.6% p character. You can see the formation of sp2 hybridization. Spherical shaped s orbital combines with the two dumbbell shaped p orbitals, resulting in three identical sp2 hybrid orbitals. So the angle between any two sp2 hybrid orbitals is 120 degrees. We also call it as trigonal hybridization or triangular hybridization. Now sp3 hybridization. In sp3 hybridization, 1s and 3p orbitals of almost equal energy intermix to give 4 identical and degenerate hybrid orbitals. These 4 sp3 hybrid orbitals are oriented in tetrahedral symmetry with 109 degrees 28 minutes angle with each other. The sp3 hybrid orbitals have 25% s character and 75% p character. sp3 hybridization is also called tetrahedral hybridization or tetrahedral hybridization or tetragonal hybridization. See, one spherical shaped s orbital is mixed with 3 dumbbell shaped p orbitals, resulting in the formation of 4 identical sp3 hybrid orbitals. These 4 sp3 hybrid orbitals are oriented in a tetrahedral manner by making an angle of 109 degrees 28 minutes. sp3d hybridization. In sp3d hybridization, 1s orbital, 3p orbitals and 1d orbital of almost equal energy intermix to give 5 identical and degenerate hybrid orbitals, which are arranged in trigonal bipyramidal symmetry. Among them, 3 are arranged in trigonal plane. The remaining 2 orbitals are present above and below the trigonal plane at right angles. The sp3d hybrid orbitals have 20% s, 60% p and 20% d characters. Look at the structure of sp3d hybrid orbitals. sp3d2 hybridization. Intermixing of 1s, 3p and 2d orbitals of almost same energy by giving 6 identical and degenerate hybrid orbitals is called sp3d2 hybridization. These 6 sp3d2 hybrid orbitals are arranged in octahedral symmetry by making 90 degrees angles to each other. This arrangement can be visualized as 4 orbitals arranged in a square plane and the remaining 2 are oriented above and below this plane perpendicularly. Look at the formation of 6 identical sp3d2 hybrid orbitals. Now look at the sp3d3 hybridization. sp3d3 hybridization. In sp3d3 hybridization, 1s, 3p and 3d orbitals of almost same energy intermix to give 7 sp3d3 hybrid orbitals, which are oriented in pentagonal bipyramidal symmetry. 5 among the sp3d3 orbitals are arranged in a pentagonal plane by making 72 degrees of angles. The remaining are arranged perpendicularly above and below this pentagonal plane. Look at the formation of 7 sp3d3 hybrid orbitals. So, for sp3 hybridization, let us take the example of molecules. For sp hybridization, formation of CO2 molecule, C2H2 molecule can be taken into consideration. For sp2 type of hybridization, formation of BF3 molecule, C2H4 molecule can be taken into consideration. For sp3 hybridization, formation of methane, CH4, ethane, C2H6, ammonia, NH3, water, H2O may be taken into consideration. For sp3d type of hybridization, formation of PCl5 molecule may be taken into consideration. For sp3d2 hybridization, for sp3d2 hybridization, formation of SF6 molecule, sulfur hexafluoride molecule may be taken into consideration. For sp3d3 hybridization, formation of IF7 molecule means iodine heptafluoride molecule can be taken into consideration. Thank you.